Good.
Thank
I
you.
find the clicker here. Is this the clicker? Thank you. Well, Betsy, I'm only 75, so I mean, you know, I tend to wonder rather than sit behind the lectern. So let me start today, if I can figure out what which button the clicker works. It's not that button. That button. I'll talk a little bit about EMP, but first let me tell you something about my beliefs. I think that climate change and ocean acidification are probably the two biggest existential threats that we as a society face. And we haven't been able to do anything about it. Most of us know the theory of ocean acidification, climate change. I always tell people, look, if you don't believe in, I've actually given when I was at WVU, gave my fire and brimstone version of the speech to the West Virginia Coal Association Executive Committee, which was neat. But tell them, you know, if you don't believe in climate change, you probably should go back and retake freshman physics. For ocean acidification, high school chemistry will do. It's that simple. There's nothing there. If you look at the top of the atmosphere, we're down about 0.6 watts per square meter. If you look at the energy coming in and the energy going out, because it's being absorbed on the way out. Being absorbed right where carbon and methane would absorb things. If you integrate that around the world, say, what's the total energy up there? It comes out that the energy coming in versus the energy going out, we're trapping the equivalent of about 3 to 4 Hiroshima and Nagasaki sized bombs every second. That's the amount of energy. So this is a huge thing, but we don't seem to be able to get a grip on it. So what we'd like to describe today, we think does get a grip on it, and it will present a solution that people can get behind, actually make money, do society some good other than climate change and ocean acidification. So the first threat, that's the climate change, and I think everybody in the room, probably especially the board members of the Climate Institute, agree on that. But the second thing is EMP, and I would like to thank Kim Jong-il for probably making my day on that one. But in the early nuclear test on Johnson Island in the Pacific, they actually disrupted electric circuits in Hawaii 800 miles away. And this wasn't a big bomb. This wasn't one designed to throw off EMP. It was a normal, if you can have such a thing, nuclear weapon. There was a big solar flare hit down in Quebec and fried transformers in the eastern US. And when I say fried, I mean fried. It really, when you cook a transformer like that, it stays cooked, if you will. Let me show you what I mean. If you have a flare, if you have an EMP, if you have any kind, you know, wireless, we have EMP right here. My cell phone's working on wireless. That's many, many, many micro EMP. But the voltage induced is A, the strength of the EMP, B, the length of the wire that it hits. It's so many volts per meter. Well, what if your wire turns out to be like 1,000 miles long? You're going to get a big voltage. And so when you fry a transformer, it's going to stay fried. Now, the problem with transformers is they don't fail, usually. Utilities have tons of them. They'll last 50 years. They don't have any moving parts. They just sit there. And as long as you don't overload them, they're fine. So no one has any spares. You won't find very many spare transformers laying around. But it may take you 2 years to get a new one. And so if we were to take an EMP and destroy transformers in quite a few different American cities, we could not fix it, period, end of discussion. I mean, I've been at many utilities. You don't keep spare 345 to 138 kV transformers laying around. And so this is a real threat that the United States has, both from solar and from EMP. And I joke that's the New York blackout. We've already covered some of these things that won't work. Cell phones, how are you going to charge them? They may work for a while, but how are you going to charge them? Water, can't pump water, hospitals. And I joke there's a couple, one of them in particular, it could cause the downfall of Western civilization. During the New York blackout, one of the interesting things they found in the hotels was the keys would work because they have batteries in the door. But the little machine that makes keys wouldn't work. So that wasn't ups. But the thing they really fell out that I joke would cause the downfall of civilization was electric toilets won't flush. And at some of the big hotels in New York, they had to close the public toilets because the little buttons work on electric. If you had a flush handle, you were fine. But you just think, I mean, just think about all the things that we use. You couldn't get prescriptions, you couldn't have email, et cetera, et cetera, et cetera. And so it really is a very serious and real and threat. So for the, a lot of the military people and the people that worry about national security, this is high on their watch list, believe me. Now, one of the solutions to EMP is to underground it. And you think, why? Well, the Earth really won't shield EMP. It shields some of the EMP, but not all of it. But undergrounding has a very useful purpose, and I'll show you what it is. This is an underground 500 kV. I took that picture in Berlin. Berlin has an underground 500 kV system, and each of these, there's 3 phases on each side as usual. That's 3 transmission lines. You can walk right up and put your hand on it. It's 500 kV that far away. And the reason is the conductor. This is an overhead conductor. We call that ACSR, aluminum core steel reinforced. That's the kind you see up there. Underground conductor has, you notice all these layers wrapped around it. And if you can notice them, I don't know if you can see it, but there's a layer there of little thingies that are sort of long. That's a shield. And what happens is the EMP hits the shield. It induces a voltage in the shield, but that shield's grounded every couple miles. So A, you don't get much voltage because it's not that long, but B, it goes right to ground. So it doesn't bother the conductor itself. And so that's why underground is shielded and it will defeat EMP. It's already been pointed out, if you're really going to move power long distance, can you do it with AC? Yeah. Is it a lot easier with DC? Also, yes. It's just if you're going to move massive amounts of power for stuff like what we call VARs, reactive power, magnetic fields circling the wires and electric fields, it's just a lot easier. If you do it with DC, DC is already becoming the preferred method of transmission for long distance power. There's big DC lines, the so-called Northern Pass line coming down out of the lines coming down out of Quebec. There's a big DC line now and coming from Oregon down into California. So for long distance, it's already becoming the preferred method. And so as we go from there, I'm going to talk about 2 cities. This, I think, I don't actually know where that one was, but you're well aware of that. The other one is I live in Tucson. I took that picture in Tucson. It was 90 in Tucson the other way just to rub it in, although the weather's wonderful here today. Let's look at Cleveland. Let me discuss what I'll call the Cleveland effect. Consider Cleveland, 5 really yucky, overcast, rainy, snowy, sleety, whatever days with no wind. How are renewables going to work? But then let's assume that we have one brilliant, sunny, windy day with like 40-knot winds, whatever the maximums the windmills could take. But then we have 5 more yucky days. Well, everybody realizes we've got to have 5 days of batteries to ride through that. What most people don't realize is you have to have 6 days of generation if you're using pure renewables. 1 day to generate on the sunny day, the other 5 to charge the 5 days of batteries. Well, no one's going to do that. And so in places that don't have really, really good profiles for wind and solar, you'll start migrating towards renewables. We've got to do that. But you'll also migrate towards a heck of a lot of gas turbines because no one's going to put in 500% reserves in batteries plus 500 in generation. It's a lot easier to throw in a gas turbine. So in areas like Phoenix and Tucson, I really believe that within just a few years, we will be able, using solar, to almost displace fossil fuels, solar plus batteries. Because the sun shines, and then we'll have peak hours from like 6 p.m. till 9, and then the load drops way off. The load in Tucson and Phoenix have the advantage that they're coincident with solar. Okay, when the sun goes up, the load goes up because it's air conditioning, but so does the generation. So I think, within the next few years, but that's not true in Cleveland. What a national grid will do is give you the opportunity then of bringing solar to Cleveland because it will displace gas. It's cheaper. It has 0 fuel cost versus 2 or 3 cents fuel cost. So if you can get the solar there, it will displace gas. Otherwise, we'll still be burning gas. Now, gas is good. It only uses 40%, or only emits 40% of the carbon dioxide as coal does, but it's still emitting carbon dioxide. If we want to go to a high level of renewables nationwide, it is imperative that we have a national grid. Or we have a whole bunch of batteries, which isn't going to work. Nobody's going to put those in. They'll be too expensive. So the first thing the national grid does is it will allow us to get to a very high percent. I think we can get up to 80, 90% penetration of renewables with a national grid. Some people may disagree, but okay, settle for 70. I'd rather have 80 or 90 because of grandchildren, but we need to do that. Now, the next city we'll discuss is Phoenix. And you think, well, Phoenix doesn't need a national grid. I put this in the incidentally picture of a transmission tower. If you ever get a picture of an underground transmission tower, it looks like a vacant lot. So anyway, I know we're talking about underground, but I had to have something. Phoenix, if you think, well, okay, you could cover all of Phoenix, the entire metro area of Phoenix with solar cells. You probably wouldn't generate more than 10% of their energy because they're just not the watts per square meter. And so even in a city like Phoenix, or a city that has a very high wind, you ever see any rooftop wind? Okay, no. The answer, I mean, maybe somebody has one. But actually, I do a lot of work at Arizona State University, and they actually have some rooftop wind. They're little teeny things. But the point is that if we're going to go to high penetrations, even in cities like Phoenix, we've got to put the solar out here and bring it in with the grid. And so to me, it's critical, and that's the way we get to a high penetration of solar. Now, people say, oh, you're going to have 5 to 10% losses, maybe 15. Yeah, that's probably right. I don't know. I squared R, you can figure it out. It's not that. It'll be one thing on one day and one thing on another day. Let's look at losses. If you're going to compare two systems, you can't compare one system and another and just look at one set of losses. Let's look at all the losses. Let's look first at a coal plant. First off, coal plants are only about 35 to 50% efficient. The old ones are 35. That means for every 3 megawatts of energy you put in, you get 1 out, 2 go up in losses. How's that for losses? Right off the bat, 65%. What's the losses in transmitting the coal? With a solar plant, you don't have to transmit the fuel to the plant. You got to take the plant to the fuel, but nature does the job of getting the fuel to the power plant. Coal plant, what's the losses in transmitting coal? What about ash spills, et cetera? What's the loss when you store gas underground? What about the losses in drilling, the methane emissions? What about the little bug? You think, why is the little bug there? The little bug is to remind me, because I'm terribly forgetful, about what we call parasitic losses. In a modern coal plant with pollution control equipment, your losses for running the plant, the PCO, all the different equipment is going to be 10 to 15% right off the top. And of course, since the coal plant's only 40% efficient, you're going to need 2.5 times that in terms of fuel to run those pieces of equipment. What's the losses in the compression losses in bringing gas? That's the Alaska pipeline. What's the pressure, the losses in compression from bringing gas up from Texas to New York? And what's the loss in mining? There are losses in everything. I would submit that the losses in a national grid are far less because, for one thing, the losses we're talking about, solar isn't that efficient when you convert it. Wind, there's a law that says you can only get X% out of a windmill because you got to have wind going out the other side or there'll be back pressure, so you can't get all the wind. And so I would say that it's going to be less. And plus that, the losses we're talking about are from free fuel with no pollution, no et cetera. We think the total project cost of building this would be under $500 billion. You think, oh, that's a lot of money. Yeah, it is. But according to EEI, where I was a board member for years, the total spend on transmission right now is $20 to $25 billion a year. Every year, we spend that much on transmission. Project can be built in stages. We're already starting it. It's not a national high voltage DC, but for instance, consider Four Corners, Four Corners, Colorado, Utah, Arizona, and New Mexico. There's 3 big power plants up there, Navajo, San Juan, and Four Corners. Navajo is already scheduled to shut down. Well, there's a lot of coal energy going from Navajo to Phoenix, LA, Denver, and Salt Lake. As that plant goes down, those lines free up. Then you can get power from Phoenix, solar power, up through those lines to Denver, Salt Lake, LA. So you don't have to build this all at once. This ought to be a goal, though, that we set a national policy. And it's got to be national. You can't do it just locally and get the optimum results. And so many DC lines already operate. They're connected to the AC system. Private financing, utilities can build it and earn on it. Public-private partnerships, the federal government infrastructure, DOE loan guarantees. And we can't only look at the cost. The fuel savings, every single year, if you look at EIA, the power industry spends about $30 billion a year on natural gas, $30 billion a year on coal. That's $60 billion. That's a savings that this won't totally displace, but hopefully it can displace in 20 years 90% or so of it. Another big one is capacity factor. You talk about, Betsy talks about windmills. You look at solar. Well, if you put a solar panel in Cleveland, it's not going to run like a solar panel in Phoenix. TEP, where I was the CEO, just signed an amazing contract for solar, very cheap. Why? Because the solar panels can run 12 hours a day for almost 365 days a year. I hate to rub it in, but we only have 11 cloudy days a year, and those aren't very cloudy. And so if you put a solar panel in Cleveland, it may only run 200 days a year. In Tucson, the capacity factor. So the national grid gives you the ability to put your power plant, your solar panel, where it'll run better. And that lowers the overall cost, because the cost of solar is just how many kilowatt hours, total cost divided by the number of kilowatt hours. Kilowatt hours go up, costs go down. And so that gives you a huge capacity factor increase, which makes the energy even cheaper. So I think that's important. And clearly the loss of pollution. This must be national. I always talk about optimizing the human body. If you jump into the human body and you say, I'm going to optimize, and you make the heart pump as fast as you can and the adrenal gland put out as much adrenaline as you can, you're going to be dead in about, I don't know, I'm not a doctor, but 2 minutes, 5 minutes, you'll be dead. To get an overall optimum, you must optimize the whole system. And that's where we must have federal policy. We need the military, the DOE. This won't cost any more than building out our system anyway. And so why don't we build it to achieve the goals of EMP and to achieve the goal of reducing climate change and ocean acidification. So thank you.